to the video. So today we're going to continue with subtopic 14.3 thermodynamic works. How does a thermodynamic system do works? If the piston compresses the gas as it is moved inwards, work is done on the gas. W is negative. As the gas expands against the piston, it exerts a force through a distance and gas does work on the piston. W is positive. Let the gas pressure on the piston face be P. Force exerted on the piston due to the gas pressure is force is equal to pressure times area. As the gas expands, the piston is pushed outward an infinitesimal distance dx. The area of the piston times with the change in the horizontal distance will give you the change in volume dV. dV is equal to A dx. The work done by the gas is dW is equal to F dx. Since force is equal to PA, therefore F dx can be written as PA dx. And the area times the change in distance will give the change in volume dV. So now we look at the variation of the pressure against the volume for a system showing below. As the gas expands against the piston, the pressure decreases and the volume increases. For a small change in volume, gas does work against the pistons. dW is equal to PdV. For a finite change in volume from initial to final point, we can integrate the equation to find the total work W. So integrate both sides. dW is equal to the integration of P dV. We will get the total work done W is equal to the integration of P dV from the initial to final volume. This is equivalent to the area under the PV curve. During the expansion, the work done is positive, and during the compression, the work done is negative. So work done in isobaric process. In the isobaric process, the pressure remains constant. Therefore, we can use the equation W is equal to the integral of P dV to calculate the work done in isobaric process, or to get the correct formula for the work done in isobaric process. So since pressure is constant, therefore it can be taken out from the integral, so we just left with the integration of dV. Integrate dV, we will get V with respect to V1 and V2. Solve the equation, we will get W is equal to P times with the change in volume. Work done is also represented on the PV diagram by the area under the process line, which is the area shaded in yellow. Next, work done in isovolumetric process. In the isovolumetric process, volume is constant. Therefore, no change in volume, dV is equal to 0. Hence, no work is done during the process. As you can see from the graph over here, there is no area under graph as well. So work is equal to 0. In the isothermal process, temperature T is constant. So from the graph, the area under the curve will give you the total work done. The first graph for A is the isothermal expansion, since the volume 2 is bigger than volume 1. For the graph in B, this process showing the isothermal compression. To get the correct formula for the work done in this process, again, we're taking the formula of W is equal to integration of P dV. We can substitute the formula for P as equal to nRT over V from the ideal gas law equation. Hence, W can be written as the integral of nRT over V dV. Number of moles, gas constant, and temperature are constant. Therefore, it can be taken out from the integral, so we just left with the integration of 1 over V dV. The integral of 1 over V dV will get ln V. So ln V, we can written as ln V2 minus ln V1. Therefore, we will get the equation for the work done in isothermal process as W is equal to nRT ln V2 over V1. Since temperature is constant, we can apply Boyle's law. P1 V1 is equal to P2 V2. Therefore, rearrange the equation, we will get V2 over V1 is equal to P1 over P2. Hence, W can be written as nRT ln P1 over P2. So now we look at the summary of all the thermodynamic process and the first law involved. For the first one, isothermal, the physical quantity that remain constant is the temperature. So first law predicts as the temperature constant, so delta T is equal to 0, it will make no change in the internal energy as well. So delta U is equal to 0, hence Q is just equal to W. From the derivation, we know that W is equal to nRT ln V2 over V1 for the thermodynamic works. The second process is the isobaric. The pressure is constant. So first law of thermodynamic Q is equal to delta U plus work, and from the derivation, W is equal to P delta V. The next one is the isovolumetric process. Volume is equal to constant. So as volume is constant, so no change in volume, delta V is equal to 0, it will make W is equal to 0. So Q is just equal to delta U. The last one is the adiabatic process. Q is equal to 0. No heat is transferred into or out of the system. Since Q equal to 0, first law predicts that delta U is equal to negative W. So these are all four types of graph for the isothermal process, isovolumetric, isobaric, and adiabatic process. So now let's do an example. Example 3, an ideal gas expands to 10 times its original volume. Maintaining a temperature of 440 Kelvin, the gas does 3.3 kilojoules of work. How much heat does the gas absorb? So from the questions, we can see that the temperature is maintained at 440 Kelvin. Therefore, we know that the process is isothermal. So we have to use the first law of thermodynamics, Q is equal to delta U plus work to find the heat used. Since temperature is constant, therefore delta U is equal to 0, hence Q is equal to work is equal to 3.3 kilojoules. B. How many moles of the gas are there. So the question asks to find n number of moles. So we can use the formula of work done for isothermal to find the number of moles n. So substitute all the information given. So W is equal to 3.3 times 10 to the power of 3 is equal to n number of moles times with the gas constant 8.31 times with the temperature 440 ln final volume, which is the 10 times bigger, over the original volume V1. So we can get N is equal to 0.39 moles. So now you may pause the video and try to do the question by yourself.